So now that we've seen that when working on a finite dimensional vector space, transformations can be thought of as working on a list of real numbers that are the weights of the linear combinations giving our various vectors. We see that it's important for us to understand how to work with these lists of numbers. So in that vein, let's ask if this vector is an element of this vector space. All the vectors on the board are elements of R3, the set of ordered triples of real numbers. Okay? But that doesn't mean that the vector space on the right, span of these four vectors, is R3. It might not contain some elements of R3. It's definitely a vector space, but it might be a subspace of R3 rather than all of R3. If it was all of R3, then this question would be easy to answer. Clearly, 9, -7, 13 is an ordered triplet of real numbers. So it is in R3. But that doesn't mean that it's in this vector space. In order to answer this question, we need to find weights for which this works. All right? When written in this form, it's called a vector equation. We can also say this is a linear combination of these four columns. So it could be the output of matrix multiplication. Which is often written as A x equals B. All right? We can also just view it as a system of 3 equations in 4 variables. All right? These different perspectives can all be lucrative in their own ways. All right? In order to actually answer this question, it will be easiest for us to work from this form, writing it as an augmented matrix. So I'll have all right, there's my augmented matrix. Notice that it's really just this system where I just didn't write the x's, the pluses, or the equal sign. Notice also that this is just matrix A here. Augment bar, and then the vector that I'm looking for, whether or not it's in the span of these. That will be a useful perspective for us to have going forward. The vectors to the left of the augment bar are the ones that we're forming a linear combination of. The vector to the right of the augment bar is the one that we're trying to write a linear combination that equals. Okay? So here I'm asking for a linear combination of these four vectors that equals this vector. Okay? All right. Now, it's important for us to remember in what follows that each of these rows represents one of these equations. So anything that I could do to this system of equations, I can do to these rows. All right. Now our goal here will be to simplify this system as much as possible. To that end, we're going to be trying to make as many zeros as we can. Philosophically, a zero in a column means that the variable associated with that column does not appear. All right? So we begin by choosing an element of the first column to elevate to pivot status. Okay? So this is going to be a pivot. Now, in this system, I could replace the top equation with the top equation plus 2 times the second equation. All right? And the new system will have exactly the same solution set as the old system. So in my augmented matrix, I could replace row 1 with row 1 plus 2 times row 2. In doing so, this 2 will become 0. Similarly, I can replace row 3 with row 3 plus 4 times row 2. That will cause this number to become 0. So let's see what happens. Row 1 plus 2 row 2. 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 Row 2 stays the same, although I'm going to change its sign because I can. Think about what that would mean. I would multiply the second equation by -1. I can multiply the second equation by -1. That's no problem. So that means I can multiply the second row by -1. Row 3 plus 4, row 2. 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 All right? So remember, pivot. All right, now let's take a minute or two to think philosophically about what has just happened. This pivot has cleared its column. That means that the variable x1 now does not appear in any equation except equation 2. Equation 2 can now be thought of as dedicated to x1. Equation 2 will definitely be satisfied because x1's value is determined exclusively by what it needs to be in order to satisfy equation 2. x1 is, for this reason, called a basic variable. It is determined. All right? Its value is fixed by whatever it needs to be in order to satisfy equation 2. Now, as I go to the second column and look around for pivots, I see that the only non-zero element of that column is the 2. But once again, philosophically, it would be inappropriate for us to now promote the 2 to pivot status. We would effectively be saying, now we're going to dedicate equation 2 to x2. But that's not appropriate. You can't dedicate an equation. This equation is already dedicated to x1. So the fact that there are no viable pivots in the second column is going to imply the second column simply does not have a pivot. x2 is not a basic variable. Its value will not be determined. Okay? All right, so that's fine. Moving on. I can elevate the -1 in the third column to pivot status. And if I do that, I can clear its column. All right, row 1 stays the same, although once again, I'm going to change its sign. Row 2 goes to row 2 plus 2 row 1. 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 Row 3 minus 3 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 row 1, row 3 minus 3 row 1. All right, now let's look at what happened here. If I now go to the fourth column, I see that there are no viable pivot options. So these two columns lack pivots. Philosophically, that means that their values are not determined. They're not basic. Since their values are not determined, we call them free variables. I like to give them other names. I'm going to call them S and T. So S and T are free. All right? So we'll see what that means in a minute. But for now, a column that lacks a pivot is associated with a free variable. What about a row that lacks a pivot? This last row now lacks a pivot. Well, let's think again philosophically. These pivots in these rows meant that x1 and x3 have values that are determined. What did we mean by that? What we meant is that the value of x1 is whatever number it needs to be to cause the second equation to be satisfied. If I turn that on its head, that implies that the second equation will be satisfied. The pivot in column 3 implies that the first equation will be satisfied. But there are no pivots in the third equation. Okay? Now, of course, in the row reduction process, any non-zero number in a row to the left of the augment bar can be used as a pivot. So a row that lacks a pivot means an equation that doesn't have any variables in it. 0x1, 0x2, 0x3, 0x4. So there is no variable that's there to enforce its validity. An equation that lacks a pivot, or a row that lacks a pivot, is either satisfied or not satisfied. There's no variable that can be used to cause it to be satisfied. Now, in this case, the number on the right of the augment bar is a 0. So this last equation, even though it lacks a pivot, is satisfied. It reads 0 equals 0, and 0 does equal 0. But if this number here had been 16 instead of 15, all the choices that we have made here would still be the same. Those choices are dictated by what happens to the left of the augment bar. But this number would not have been 0. And that would mean that our third equation would be invalid. Okay? So, a row that lacks a pivot implies that there could be no solution at all to the system. Okay? All right, now let's go ahead and write out our most general solution. If I RF this matrix, I'll get this, and I can write x1 plus 2s minus t is equal to negative 3 x2 equals s, x3 plus 2t is equal to 5, and x4 is equal to t. All right? If I now solve, I've got my most general solution as that one. Or if I wanted to, I could rip it apart and write it as that. Now, the first thing that we see here is that the answer to the question is yes. But we also see that we can write this vector as a linear combination of these four vectors in an infinite number of ways. S and T, as we said before, were free. Their values are not determined. They could take any value from negative infinity to infinity. All right, so that implies that these vectors are linearly dependent. We can also see that in a very, very easy way from this augmented matrix. Using this interesting ability we have to move the augment bar. Suppose that the augment bar was here instead of there. So now I'm asking, is this vector a linear combination of these three? The answer would be yes. Yes, it is. This vector is -1 times the first vector plus 2 times the third vector. And indeed, if I do 2 times that minus that of 4, Negative 4 plus 1 is negative 3. 10 minus 4 is 6. All right? So the fact that this system has solutions implies that this is a linear combination of these three. What if I moved it again? Now, I'm asking, is this vector a linear combination of these two? And the answer is no. Because the second equation in this case would read 0 equals 1. And 0 does not equal 1. Okay? So kind of an interesting take on the augmented matrix. It gives us a nice way to think about how these systems work. Okay? So, linearly dependent. That means that there's a non-trivial linear combination of the four vectors giving 0. All right. See if we can flesh that out a little bit. Let's call this vector x naught, this vector n, and this vector m. Okay? What we found is that matrix A acting on this vector gives 9, negative 7, 13, regardless of the values of S and T. Now, matrix multiplication is a linear operation. In fact, we can think of it as the only linear operation on a finite dimensional vector space. Okay, by the way, I keep saying that. Let me give you an example of a linear operation on an infinite dimensional vector space, the derivative. The derivative operator acting on a sum of two functions gives the sum of the derivatives. And the derivative of 13 times a function is 13 times the derivative of that function. Okay? Despite that fact, I can't always think of the derivative operation in terms of a matrix because it acts on an infinite dimensional vector space. We'll have more to say about that later. But because matrix multiplication is linear, I can distribute this. So we get 9, negative 7, 13, regardless of the values of S and T. And the only way that that can possibly be the case is if A acting on N and A acting on M are both 0. And in fact, if I do negative 2 times the first vector plus 1 times the second vector, I'll get 0. That gives me a non-trivial linear combination of the first and second vectors that gives 0. Okay? Similarly, we have a non-trivial linear combination of the first, third, and fourth vectors that gives 0. If you think about it, all of this is associated with the fact that we had a column that lacked a pivot. It meant that that column was a linear combination of previous columns. So if I subtracted there, I would get a non-trivial linear combination that gives 0. All right? So that's a pretty fleshed out example of a numerical linear algebra problem.